Hello, this is Jack Jackson. This video we're going to be talking about solving trigonometric equations. So the idea of solving conditional equations is one of the most basic standard types of problems that we have. You see many examples in algebra classes, such as linear equations, for example. And we might have something like this. And it's kind of like a murder mystery. Who done it? Find out which x's make this true. Of course, you guys already know how to do this. We subtract 4 from both sides of the equation to get 3x equals 6. Divide both sides of the equation by 3 to find x equals 2. Of course, we're obeying that golden rule of equations. Thou must do unto one side what thou dost to the other side. Now, we can also visualize this. If we solve this for 0 on one side, get some function equal to 0. So in this case, subtract 10 from both sides. We would get y equals 3x minus 6. And we want to set that equal to 0. If we'll graph y equals 3x minus 6, we get, in this case, a straight line. And of course, what we're interested in is finding the x value where that crosses the x-axis. And of course, once again, that's x equals 2. Of course, you've also done this for things like quadratic equations as well. For example, here, 3x squared plus 4x plus 5 equals 4. Once again, we could subtract 4 from both sides to get it equal to 0 on one side. And the idea here is we want to factor it. So if we use, I call it anti-FOIL factoring, then we get it factored this way into two binomials. Check out, use FOIL distributive property to go ahead and figure out to see that that is correct. And then set each factor equal to 0. We have a certain property that of 0 that says a times b equals 0, either a equals 0 or b equals 0. It's a special property that 0 has. And solve each one of those. In the right one, we subtract 1 from both sides. In the left, we subtract 1 and then divide by 3. So we see either x is negative 1/3 or x equals negative 1. If we take this version where it's already solved for 0, y equals 3x squared plus 4x plus 1, graph that, we see that it does cross the x-axis at negative 1 and negative 1/3. And so those are our two solutions. We'll do one more from algebra. How about a polynomial equation? We've got x cubed minus 3x squared minus x plus 3. This is already solved for 0. How do we factor that? Remember how to factor that? Well, one way we can do it is by grouping. We group two terms and two terms. Out of the first one, factor out a common factor of x squared, and out of the second one, factor out a negative 1 using the distributive property. And if you look, the remaining factor is x minus 3 in both cases. Factor that x minus 3 out, and we're left with the x squared minus 1, which is the difference of two squares, factoring as x plus 1 and x minus 1. Now, this one has three factors. Set each of the three factors equal to 0 and solve them by adding 3, negative 1, and 1 respectively to both sides. And so we get x equals 3 or x equals negative 1 or x equals 1. Or we can sort of condense the notation a little bit if we write it this way. X is an element above, that symbol is an element of, the set negative 1, 1, and 3. We can put those in any order we want. I just happen to put them in increasing order. From a graphical standpoint, if we were to graph this function right here, y equals x cubed minus 3x squared minus x plus 3, we see that it crosses the graph 3 times. So we've seen an example where it crosses the graph 1, 2, and 3 times. So you've done this sort of thing over and over again in your algebra classes. You've solved many types of equations in this point in your mathematical careers. You've solved linear equations, quadratics, polynomial equations, probably rational function equations, power function equations, radical equations, exponential equations, maybe some logarithmic equations, and so forth. So why are we so interested in solving equations? Why is that one of the main things that we do in algebra? Well, it's because solving equations is a critical step in solving many real-world applied problems. So that brings us to today's lesson on trigonometric equations. So it's natural that we should want to also be able to solve equations that have trigonometric functions in them. Now, before we get going too far into this, Let me ask you a question. What is the main difference that we have noticed about trigonometric functions compared to other types of functions that we've studied? You know the answer to that? What do you think? Well, it's that trigonometric functions are periodic. So trigonometric functions are ultimately based on circles, so they have a cyclic pattern to them, repeating pattern. This is actually the main reason that we study trigonometric functions. We use them to model real-world situations where things go in repetitive cycles. So what does this have to do with the number of solutions to trigonometric equations? In other words, the number of x-intercepts of a trigonometric function. Well, algebraic equations have a finite number of solutions. Examples we looked at had 1, 2, or 3 solutions, but they have a finite number of solutions. Trigonometric equations typically have infinitely many solutions, and they're arranged periodically. Now, actually, we have already solved some trigonometric equations in this class. When we first started graphing trig functions, like f of x equals sine x, we looked at a picture something like this, where we started with a unit circle picture where the, say, sine of theta, where theta is the arc length here along the unit circle, the radian measure of that amount that that point P spins when you sort of flick it and spin it around here. And we transferred that over to this picture here. Well, if this is going around a unit circle, the y value of that point is the sine of that angle. Of course, it's just opposite over hypotenuse in this little reference triangle. So that extends what we know about trig functions of a acute angle to just trig functions of any angle. And this arc length here, of course, is just the x value over on this graph, but the y values are the same. Well, what happens when you make it all the way around the circle? Then you've made it through what we call one period of this wave from 0 to 2 pi, and then it just starts repeating again and again and again and again. So we get a wave that goes on forever. If the spinning is in the negative direction, well, that's just going to make the wave continue to the left forever as well. So we've already seen this before. And in particular, notice that there are infinitely many times that this graph crosses the x-axis. See, there's at 0, at pi, 2 pi, 3 pi, 4 pi. Go this way, negative pi, negative 2 pi. So, what are the solutions to the trigonometric equation sine of x equals 0? Or, what are the x values of the x-intercepts of the sine wave graph? Or, what are the theta angles, values over here, with a y-coordinate of 0? And notice they're at 0. We rotate to pi, 2 pi, 3 pi, or go this way, negative pi, negative 2 pi, and so forth. So either way, those three questions are really essentially the same question. And so that leads us to see that there are infinitely many times that the sine wave graph meets the x-axis. And so now we can solve that. And of course, we know the answer is this, that the sine of x equals 0 exactly when x is an element of n times pi such that n is an element of the integers. So that funky looking z there is for Zahlen, which is German for integers. So that's why it's used as z. And so this is just saying that, x is equal to n times pi, where n can be any integer. So, for example, when n is 0, you get 0. That's right here. When n is 1, you get pi. When n is negative 1, you get minus pi, and so forth. So we have already solved some trig equations earlier in the course, like this one here. So let's look at some variations on the theme now and put together some things that we know about solving the trig equations that we already kind of know about, plus the ones that we know about solving, say, some polynomial equations. Put those ideas together to solve some more trigonometric equations. All right, so let's see if we can solve this particular one. 2 sine of x minus 1 equals 0. Okay, let's start by looking at it graphically. So let's graph this function, y equals 2 sine x minus 1, that function on the left. Use your graphing calculator. If you've got a like a TI-84 calculator or something like that, go ahead and pull it out. Or maybe you have a graphing app on your phone or your tablet or computer. Go ahead and pull that out now and graph it and see where it intersects the x-axis. So I'd like to, if you're watching the video here, let's go ahead and pause the video and do that yourself right now. Okay. So first of all, you need to be sure your calculator is always in radian mode. So here's, if you hit the mode button, you want to make sure, normally these things are just sort of all on the left, but in particular this one that says radian, this is a screenshot from a TI-84. You want to make sure in radian mode. Then you type your formula in, so y equals, put 2 sine of x minus 1, and then press zoom, and if you'll press zoom 7, which is zoom trig, you'll get a graph that looks like this. So see if you can go ahead and get that, especially if you have a TI-84, you can make it look just like this. This zoom trig will sets up a standard window where the marks, the little hash marks or tick marks on the x-axis are spaced out at a spacing of pi over 2. So this is 0, pi over 2, pi, 3 pi over 2, just off screen is 2 pi, and so forth. And going up and down, the marks are in ones. So this is 1, 2, 3. And so we can see a graph there. And so, of course, what we're looking for are these places where it crosses the x-axis. At this point, at this view, we can see 4 of them. But there's not just 4. There are actually infinitely many of them. If we want to see a little bit more of the graph, here's a window that we could choose. And we can see a few more periods of this function going along here. Now, just thinking back to it, sine of x we know has a period of 2 pi, so it seems like this function here would also have a period of 2 pi, and so every 2 pi you're going to see a repeat. Now, how about using your calculator to approximate the values where it intersects the x-axis? Let's just do a couple of them. Let's do these first two positive ones right here. See if we can get approximate what that is and what that is. Remember how to do this? Use calc 0. So I think its second trace is calc. Use number 2, 0. And it's going to ask you for a left bound first. So make sure you're just a little bit to the left of this point here. And press enter. Then go to the right of it a little bit. Press enter. Put it on the thing, right on the point as close as you get. Hit enter. And it'll come back with a decimal version right there. And do the same thing for the other one. Make sure your left choice is over here, maybe past this maximum here, but somewhere in here. Right choice over in here, get it close to there for the guess, and we get those. So we have approximated both of these. So we've now approximated the values for the solution on one period, and all the other solutions are just shifts of these two solutions by integer multiples of 2 pi. Of course, we don't know the exact value of these points yet, but we do have a decimal approximation for them. So how can we find exact solutions algebraically? Let's go over that now. Sometimes it's helpful to do a little substitution. So here I'm going to let u be equal to sine of x. So that transforms the equation into a simple linear equation like this. So this will be 2u minus 1 equals 0. Okay. Now just solve that for u. We know how to do that. It's a pretty simple linear one. Add 1 to both sides. 2u equals 1. Divide both sides by 2. U equals 1/2. Of course, we're not done. We now have to substitute back in, put a sine of x where the u is. So that gets us to this point. Now, this one should look somewhat familiar to you. This is sort of one of our usual suspects here. Do you remember an angle whose sine is 1/2? Now remember from the unit circle picture, or not necessarily the unit circle picture, but any circle centered at the origin, we can figure out trig functions for that, and sine is the y value over the r value for that. So we could think of a circle of radius 2, then we want the places where the x value was 1. Okay, well this next notice that the sign is positive when y is positive, so that's going to be in quadrants 1 and 2. So there's going to be two different terminal sides that we are looking at. And basically this boils down to looking at this special triangle. We've looked at this many times before. This, if you remember this, we got this triangle by taking an equilateral triangle and just slicing it in half. Okay, so if you have an equilateral triangle, it's 2 by 2 by 2 on the outside, slice it in half. This side's 1. All the angles are the same, so that we know they're pi over 3. Then when you slice it in half, so that you have a right angle there, the other angle is half of this one, so it's pi over 6 or 30 degrees. And so that's our basic triangle. So basically what we want to do now is we want to take that triangle and we want to place it inside of a circle of radius 2 so that the right angle's on the x-axis and we get things to work out. And in this particular case, we want the y's to be 1 and the r's to be 2. So these are the two places you can put it. There's one in the first quadrant like this, and notice that this is the smaller of the two angles. So that's pi over 6, 30 degrees. And this one, the reference angle is pi over 6, but it's pi all the way here. So it's pi minus pi over 6 is 5 pi over 6. Well, that's the shortest amount of rotation that you can get, pi over 6 or 5 pi over 6. But you could also, for example, spin all the way around and get 2 pi plus pi over 6. Or you could spin this way and 2 pi minus pi over 6, or so forth. So you can add multiples of pi or 2 pi to this. Okay, so what do our answers turn out to be? Well, these that have a terminal side here in the first quadrant are pi over 6 plus 2n pi, such that n is an integer. And the ones in this quadrant are 5 pi over 6 plus 2n pi, such that n is an integer. If you wanted, there are other places you could use instead of the 5 pi over 6 or the pi over 6. I just chose the ones that are the shortest rotation to get there. So there are actually infinitely many solutions, not just pi over 6 and 5 pi over 6, but infinitely many ways that you can rotate around this. Now let's see how we can illustrate our solutions like we did our earlier equations, but doing it on a Cartesian wave graph. Here we have y equals 2 sine of x minus 1. We graph it, and we can see that the red places here are the ones that are the red ones down here, and they correspond to this over here on the circle picture. And the blue ones, or the green ones rather, are this one here. So if we wanted to check them against our earlier approximations, notice that if we take a graph here, once we've done our calc intersect or calc 0 here, if we type x, say quit, and to do x at the home screen, it gives you that value. Do pi over 6 is the same. And if we check this one, we can see that it is 5 pi over 6 like we thought. So they do check out, and we could check out the other ones as well. Now sometimes you'll want to list out all the solutions, say in a certain interval, say from 0 to 2 pi or negative 2 pi to 2 pi, or I decided to do them, all of them between negative 4 pi and 4 pi. And here you can see them. The ones underlined here, pi over 6 and 5 pi over 6, are when you let n be 0. If you let n be 1, you're adding 2 pi, or that would be 12 pi over 6 to pi over 6 is 13 pi over 6. That gets you over to here, the distance of 2 pi to the right. If we were to let n be 1 here, again, that's 2 pi is 12 pi over 6 plus 5 pi over 6 is 17 pi over 6. That's going from here to here. You can see that matches up with the scale here. That's 2 pi from here to here. Similarly, we could let n equal negative 1. We get these, and we get these two with n equals negative 2. All right, let's do a couple more examples. Here we have 2 cosine square of 3x minus 3 cosine of 3x plus 1. Start by substituting to turn it into algebraic equation. let u be cosine of 3x or cosine theta. We have 2u squared minus 3u plus 1. Set it equal to 0, which it is, and factor it. This factors as 2u minus 1 times u minus 1. Set each factor equal to 0. There we go. Solve each one of these. U is 1/2, add 1 divided by 2, add 1 here, u is 1. Now, but u is cosine theta, so cosine theta is 1/2, or cosine theta is 1. Now we need to look back and see if we can find exact values for these by using our circle pictures. So let's look here. We want the cosine to be 1/2, so this time the x is 1 and the hypotenuse, the r, is 2, and cosine is positive in the first and fourth quadrants. So our reference triangles are here. That's the same triangle we just looked at in the last example, just turned a different way. Okay, and what angles are those? Well, this is the of the angles here, that's the larger angle, which is pi over 3 or 60 degrees, or minus pi over 3 is one way to get there. Okay, so that gets you those things, pi over 3 or minus pi over 3, both cases plus 2n pi, where n is an integer. Or what do we get for the other one? Here we could use a unit circle, and notice that we want the x value to be 1, where there's only one place that happens right here, which is at 0, or multiples of 2 pi added to that, 0 plus 2n pi, or just 2n pi. And so there's our complete set when we put them together. Now these are the values in these pictures for theta, but theta is 3x. So now we need to solve for x by, this is essentially like an equals here, so we're going to divide both sides by 3 to get the final answer. And when we divide by 3, pi over, we distribute here, so pi over 3 divided by 3 is pi over 9, and then we get 2n pi over 3, negative pi over 9, 2n pi over 3, and then just 2n pi over 3. So there it is, our solution set. We could give some specific values in an interval if we want. Here they are for a few periods. I think I have this for n equals 0, see, -2, -1, 0, 1, and 2. So a few different periods there. And I think you can see those particular ones in the graph here, and you can see the periodic nature. The ones at 0 right there all come from this 2n pi over 3, which came from the one factor in the previous one, and these others come from the other factors. Now, if we want, we could find decimal approximations for these. We could use some technology to check. This essentially is using technology to check. I did this graph in GeoGebra. All right, how about another example here? 2 tangent square of 5x minus 9 tangent of 5x plus 7. Same as before, let u be something. In this case, tangent of 5x is tangent of theta. So now we have 2u squared minus 9u plus 7 equals 0. That's a quadratic. We know how to solve that. Factors is u minus 1 times 2u minus 7. Set each factor equal to 0. Solve them. For u, substitute back in. So tangent of theta is 1, or tangent of theta is 7/2. For tangent of theta is 1, we're going to use this other special triangle that we have, which is a right isosceles triangle, pi over 4, pi over 4, pi over 2 triangle, or 45 degree, 90 degree triangle, where two sides are 1. Pythagorean theorem tells you the other side is square root of 2. So tangent is positive in quadrant 1 and quadrant 3. So if we place that triangle right here, we get an angle of, splits it right in half there, pi over 4. Or it's going to be on a straight line with it. Down here is the other possibility. Different ways we could do this. One way is write it as -3 pi over 4 would be the shortest way to get there. Or you could do it as 5 pi over 4 if we're going in the positive direction. Okay? Well, it turns out those are just off of each other by pi. And of course, we know that the tangent function is period pi, so we could just take the pi over 4 plus n pi. We'll get all of those, get both of these here. Now this one over here, tangent of theta equals 7/2 is not one of our special angles, so the best thing we can do is get the one that's in the first quadrant, which is arctangent of 7/2, and then just say add multiples of pi there. So putting those together, we see that theta, or 5x, is either pi over 4 plus n pi or arctangent of 7/2 plus n pi, where n is an integer. But notice we haven't solved for x yet. Divide both sides by 5 here to get x by itself. And divide by 5, x over 4, divide by 5, that's x over 20. Then we got n pi over 5. That's like 1/5 arctangent of 7/2 plus, and again, n pi over 5. So we should see the period of this overall thing is n pi over 5, or just pi over 5, excuse me. And so here's what the graph looks like. And we see that here are the two solutions. So the pi over 20 stuff plus shifts by n pi over 5 are all the red dots here, and shift over by pi over 5 to get here, and shift over by pi over 5 again. And the arctan of 7/2, 1/5 of the arctan of 7/2 is this blue dot here, and then shift it by multiples of pi. All right, so now you've seen a few examples. It's time for you to do some. Here are some examples for you to work on. So see if you can try these. Now don't look ahead yet to the rest of the video or to the rest of the slides. Try to work these on your own. And I will have the solutions up here just a little bit later in the video, but go ahead and do these on your own first. So here's our first one. 2 sine square of x minus sine x minus 1 equals 0. Now, if you haven't done it already, you need to work this yourself. So press pause now. All right, you're back. Hopefully you've worked this yourself. So once again, real quickly, you substitute in u for sine of x. Factor, this case is 2u plus 1 times u minus 1. Just check it out. 2u times u is u squared. 1 times negative 1 is negative 1. That's negative 2u plus 1u is negative u. Set each factor equal to 0. Solve them separately. This one you subtract 1 and divide by 2. This one you add 1. Now substitute back in u equals sine of x. So sine of x is negative 1/2, or sine of x equals 1. Look at your unit circle picture here. Sine of x on the unit circle is going to be there when y is 1, which is only when the terminal side of your angle is pointed straight up. That's going to be at pi over 2 plus multiples of 2 pi. Sine is negative in quadrants. See, sine is negative when y is negative. So quadrants 4 and 3, if we're thinking about rotating negatively. And if you think about placing your triangle, your special triangle, the 30 degree, 60 degree, 90 degree triangle in there, pi over 6, pi over 3, pi over 2 triangle in there, you can see that these are the ones that it turns out to be for that. And the only thing we did at the end is just write it as one set. Either have these right here, negative pi plus 2n pi, negative 5 pi over 6 plus 2n pi, or pi over 2 plus 2n pi, where n is an integer. And we can see this illustrated. We've graphed y equals 2 sine square of x minus sine of x minus 1. And we can see here the different roots of that equation, the different x-intercepts, x-coordinates of the x-intercepts. We have minus pi over 6 is right here. And then you shift it by 2 pi, you get these other red dots here and here. The one over here, you're going to get at, minus 5 pi over 6 was this one right here. And we can shift the left and right. You can't see the one left that's off screen, but here's a couple of them to the right. And then we can take pi over 2, which is right here, and shift it, left and right to get all these. So for example, if you look at these, all the ones at pi over 2 turn out to be not only x-intercepts, but local maxima as well. Okay? And the red dots, negative pi over 6 and its shifts, notice the graph is coming down with a negative slope there, and it's coming up with a positive slope over here on the blue, where the blue dots are. All right, how about trying another one? Again, you try it without without me working it for you first. 2 cosine square of x minus 1 equals 0. Okay, you do it yourself. Press pause now. All right, hopefully you're back and you've worked this yourself. Very important that you try these on your own. Start by doing a substitution. U equals cosine of x. We have 2 cosine square x minus 1 equals 0, so that's 2u squared minus 1 equals 0. Solve for u. Add 1 to both sides. You've got 2u squared equals 1. Then divide by 2. U squared equals 1/2. Square root of both sides is plus or minus then. So u is going to be 1 over root 2, or u is going to be the negative 1 over root 2, square root. Now u is cosine of x, so we have cosine of x equals 1 over root 2, or cosine of x equals minus 1 over root 2. Okay, 1 over root 2 is positive. That is going to be a cosine. Well, positive cosine is when x is positive in the circle picture. That's going to be first quadrant or fourth quadrant. And hopefully you remember 1 over root 2 is what you get for that special isosceles triangle. So the reference angle is pi over 4, 45 degrees. So it's either pi over 4 plus 2n pi or minus pi over 4 plus 2n pi. And the one with negative 1 over root 2 is going to also have a reference angle of pi over 4, but it's going to be in quadrant 2 or 3. So the shortest route of getting there would be 3 pi over 4 or negative 3 pi over 4, and again, shifts to that by 2n pi. Well, if you look at this, that gives you all the ones with a reference angle of pi over 4, and they're all just actually rotations of each other by pi over 2. So if you look at that, then you could say the whole set of answers is just pi over 4 plus n pi over 2. And you can see that illustrated here. Notice, whoops, you have the symmetry involved in this one. This is actually has symmetry about the y-axis. So notice that we have basically all the odd multiples of pi over 4 is another way to say this. So here we have pi over 4, but also minus pi over 4. We have 3 pi over 4, also minus 3 pi over 4. 5 pi over 4, negative 5 pi over 4, and so forth. All right. How about one more? 4 tangent square of 6x plus tangent of 6x minus 3 equals 0. See if you can work this one out yourself. Again, work it on your own, see if you can get an answer, and then come back and check it after you've done it yourself. Don't just watch the video on it. Do it yourself first. Press pause now. Okay, so here's the solution. We let u be tangent of 6x. So we have 4u squared plus u minus 3 equals 0. Factor that. That's 4u minus 3 times u plus 1 equals 0. Set each factor equal to 0. 4u minus 3 equals 0, or u plus 1 equals 0. Add 3 to both sides and divide by 4 to get u equals 3/4 on the left one. Add negative 1 to both sides to get u equals negative 1 on the right. Now, substitute back in. Tangent of 6x equals 3/4, or tangent of 6x equals negative 1. Think of 6x as being your angle theta. So we have tangent of theta is 3/4. That's not one of our special triangles. That's a 3, 4, 5 right triangle, but the angle is not a particularly nice angle. So the only thing we can do is call it arctangent of 3/4. That gives you the solution in the first quadrant, and then you also have a solution in the fourth quadrant where you add pi to that or subtract pi from that. So it turns out your theta then for those where tangent of theta is 3/4, theta is arctangent of 3/4 plus n pi. Or we can say tangent of theta is negative 1. That happens in quadrant 2 or 4. Okay, so that would be 3 pi over 4 or negative pi over 4. Take your pick. I usually would say negative pi over 4 because it's the closest way to rotate to get there. But you could just also say 3 pi over 4. Either one, it doesn't matter. But then you need to say plus n pi to get the whole set. Now, once again, that's the value of theta. But theta is 6x, so you need to divide both sides by 6. So here we have 1/6 times the arctangent of 3/4 plus n pi over 6. Have to distribute here. and distribute our 1/6 here. Okay, so let's see, a 1/6 here. The 3 and the 6 are going to cancel, leaving a 2 times 4 is 8 on the bottom, and just a pi on the top. So that's pi over 8, and then n pi over 6 there. Okay, and if we look at the graph of that one, there's some looks like there's probably some vertical asymptotes here. Not probably, definitely some vertical asymptotes here going on. But in between, you can see portions of it here. There's some local minimums, local and global minima here. But for example, you can get pi over 8 is right here. It's this one right here, this blue one here. And we can also get this one over here, there, and so forth. And these are shifts by pi over 6. And then the red ones, this one here, for example, and these. So the red ones, the function is increasing. The blue ones, the function is decreasing at that point. And you can see that you get a red and blue dot on every period. The period of this being pi over 6. All right, so let me just remember that you're getting this video. Perhaps you got it from my YouTube channel. There's my YouTube channel where you can get other uh, mathematics videos. All right, have a good day.